Hello, my name is Kasey Aderhold, and I work at the Incorporated Research Institutions for Seismology. Today I will be giving this talk entitled Marine versus Land, Advancements in Seismic Deployments. I would also like to recognize my co-authors, Andy Frassetto and Bob Woodward, also at IRIS. Advances in seismic technology in past decades have taken many forms. Some of these are in sensors that are higher quality or draw lower power. Some are in data storage, which are larger volumes or more reliable. Some are in clocks with more reliable timing. Power has advanced in batteries that are lighter weight and have higher capacity. And more durable materials have been developed, as well as flotation. In emplacement, most of the advances have been on land. On land, you have better access to your sensor in order to ensure that the sensor is strongly coupled to the ground and so that you can protect it from environmental noise sources. In the oceans, it's more difficult to explore the avenues of emplacement. Most of the time, when you deploy an ocean bottom seismometer, you simply get to watch it drift to the seafloor. Due to access, emplacement advancements have largely been made on land. This has taken the form of both temporary experiments as well as semi-permanent installations, such as the transportable array, as well as permanent installations, such as the Global Seismographic Network. At sea, the two end members of temporary deployments and permanent deployments have both been explored, but to a lesser degree than on land, where you can easily access the sensor and ensure ground coupling in a variety of ways. A good way to compare emplacement techniques is to look at colocated networks. Here, we are looking at the Alaska Amphibious Community Seismic Experiment, an onshore-offshore deployment of temporary seismometers that was co-located with many permanent networks. You can see here in this plot that shows the median noise on horizontal components at 1 Hertz, that there are very big differences between the onshore stations and the offshore in the noise that they record. In these plots, blue is showing much quieter station, and red is showing noisier station. In order to compare the performance of different emplacement techniques, we will want to look at additional frequencies. Shown here are power spectral density plots for 2 offshore experiments as compared to the median of the Alaska TA in black. The 2 offshore experiments were the amphibious Alaska experiment, as well as an additional experiment called No Melt that was deployed in the Pacific in much deeper water. For the Alaska experiment, only stations that were offshore in at least 1 kilometer of water are shown. Those stations are shown in blue, whereas No Melt is shown in red. As you can see, No Melt, which was much further offshore and more distant from coastal noise sources, there is much less noise recorded on these stations, especially at the long periods as well as the high frequencies. When we compare the performance of these seismic experiments on the vertical component, we can see improvement across the board. However, in this case, the improvement in No Melt is significant. In fact, at some long periods, No Melt stations are performing better on average than the Alaska TA stations on land. Signals such as earthquakes are the reason we care so much about the noise performance of our seismic stations. Shown here are the top performers within the footprint of the Alaska Amphibious Community Seismic Experiment. These 4 stations are the quietest TA station, or transportable array station, the quietest on-land temporary vault as part of the Alaska Amphibious project, as well as the quietest shallow deployed ocean bottom seismometer, and the quietest deep water, or further offshore ocean bottom seismometer. On the left and the right are 2 earthquake signals recorded on these 4 stations. On the left is a local earthquake, a magnitude 4.2, recorded on those 4 stations. And on the right is a teleseismic earthquake, As you can see, the noise performance of these stations makes a big difference when you're trying to discern an earthquake signal. While there are processing techniques in order to elucidate the signal further, these can introduce additional factors. Significant investment can and has been made in constructing permanent seismic stations. The majority of these are on land and take the form of secure vaults or deep boreholes. Pictured here is the permanent seismic station COR in Corvallis that is operated as part of the Global Seismographic Network. Also pictured is an ocean borehole, a reoccupied International Ocean Discovery Program, or IODP, borehole offshore Vancouver Island. Nearby this ocean borehole, there is also a seafloor station that provides a good comparison to both the onshore vault station as well as this much more nearby ocean borehole station. The noise performance of these permanent installations is shown here with the horizontal components. In black is the on-land permanent station COR, which is a surface vault. In blue are the two marine installations. The solid lines are the ocean borehole, and the dashed lines are the seafloor station. Here you can see that having the additional investment in producing a borehole for the station, even in the marine environment, can get quite good results at long periods. At high frequencies, in fact, the ocean borehole outperforms the more coastal land station. Consistency and repeatability is key when it comes to seismic emplacement. In the ACES project, the deepwater offshore stations are already consistent at long periods with quite good performance. Further improvement with emplacement could bring them on par with their land counterparts. By leveraging technical advances, marine seismology has been able to narrow the gap to achieve deployment duration, data return, and timing that is on par with land seismology. Noise performance, however, remains a frontier, with similar performance possible at some frequencies, but with very few installations below the seafloor to compare to. Consistency and repeatability of at-sea installations can also be advanced. Large onshore-offshore initiatives, like SC4D, will need to consider what performance is required offshore to achieve their scientific objectives. Data used in this presentation has come from the networks listed here. We are grateful to the network operators who keep these stations running. We are also grateful to the IRIS Data Management Center for serving this data through their archive. Thank you for your attention, and if you have any questions or would like to get in touch about this project, please do email me at Kasey, Kasey, at iris.edu. Thank you.